How about this?
Yes, that's maybe a little bit.
It's better? Okay.
In the back, can everybody hear? Yes.
Can you hear me? Okay, somebody raise it then. Okay, so the topic is quantum error correction for quantum sensing. And the motivation behind it is that quantum systems are known to be very fragile against external perturbation, and that's exactly why we need error corrections. At the same time, what causes decoherence also makes them very good sensors, because if they couple very strongly to the external environment, they can also sense this external environment or any other type of signals that one might be interested in. So really, there is sort of like this duality to a quantum system being sensitive to the external environment. On one side, it's bad because it introduces decoherence, but on the other side, we can try to exploit it. And so in order to really achieve quantum sensing, what we would like to do is really to find, if you want, a contradictory solution. So what we want to do is to cancel out all interaction with the noise. So here, if I have my quantum sensor, for example, a spin, in my case, I work with NV centers in diamond, I would like it to be protected somehow against noise. So maybe it's a nuclear spin, so inherently it's very isolated from external environment. Or maybe we are doing something, so we are putting some kind of shield around it with some active control in order to prevent the noise to interact with it. But at the same time, and somehow magically, I would like to open a hole here inside my shield so that the signal can pass through and can couple very strongly to the sensor so that I have very good sensitivity. So really what we want to do all the time is to have a signal, so what we want to sense, which produce a large change in the sensor state, so a fast dynamics. It's still not working. Oh, no, it's too many. Okay, so we want this coupling to the signal to be quite strong, but at the same time, we want our quantum system to be very much isolated from other type of perturbation, which are unwanted perturbation, so that the interrogation time during which we acquire information about the signal is as long as possible. And of course, this is limited by the coherence time of the sensor itself. And so when we have these two parameters, we can achieve a signal-to-noise ratio, which is typically for a single sensor proportional to the coupling to the external signal and to the square root of the time that we are measuring. If we had something like a quantum behavior, here I would have proportionality to just like the time, not square root of time. So here I'm not even asking it to be really quantum, as if you want profoundly quantum. In general, so what I need is always a compromise. So I want to have either a strong coupling to the signal which I want to measure while I have isolation, or maybe I want to engineer some quantum error correction so that I can achieve this result. So we want to achieve some quantum error correction which cancels the coupling to the noise, to the environment, but it doesn't cancel the coupling to the signal. And very often this is difficult to achieve. The main reason is that if I want to measure something with a quantum system, let's say an atom, an NV center, a superconducting device, I use that particular device because I know it's particularly sensitive to a particular type of signal. For example, magnetic field along the z direction, so the quantization axis for my spin. At the same time, if the system is so sensitive to that particular interaction, also the main type of noise will couple to my system in more or less the same way. And so it's difficult to distinguish, to discriminate between what I want to measure and what I don't want to measure. And so this sort of poses, if you want, a conundrum which we are trying to solve here. One thing that we can try to do, as I said, is instead of just relying on intrinsic properties of my quantum system, is to try to add some layer of protection. So in general, some quantum error correction for sensing. And so what we want to do is maybe not achieve a fault tolerance for my quantum system, which is a typical objective for quantum computation, but something which is a bit more limited. At the same time, I also have additional constraints. So what I would like to do is to increase the coherence time so that I can increase the interrogation time, and this leads to improved sensitivity. But at the same time, I do not want to cancel the coupling to whatever I want to measure. And this additional constraint is not present typically for quantum computation. In quantum computation, you might have additional constraints, which are you still want to be able to operate your qubits, so perform gates in a fault-tolerant way. For sensor, if you want historical, as of, I don't know, 10, 15 years, so not so much long ago, a strategy for quantum error correction has been in the form of dynamical decoupling. It's good that Daniel talked a little bit about it this morning, so you already know something about dynamical decoupling. And the key idea here is that what you want to do is to modulate your quantum systems on a time scale which is faster than the action of the noise. So that the noise ends up being refocused, your system does not see the effects of the noise anymore. And a typical implementation has been done, in particular for dephasing noise, using just simple pi pulses. And so the typical scheme is a spin echo, or here, for example, I present a so-called CPMG variant of it, in which the evolution of the system is reversed at halfway the time or during the evolution itself, so that a phase which is acquired during one period of the evolution is reversed during the second period of the evolution itself. And this is good for canceling out noise, like, for example, this one here in purple, if the noise is quasi-static. So whatever phase is acquired because of the noise in the first half of your time is canceled out by the phase acquired in the second half of the time. Of course, if you are also trying to measure a signal which is also constant, that's also canceled out. However, if you have a signal which is oscillating in phase with the application of the pi pulses themselves, then the phase which is acquired during this period and this period adds up to the phase which is acquired into the period in between, because you have flipped the sign thanks to the pi pulses, flipped the sign of the phase thanks to the pi pulses. And so what you have is that your system now is sensitive to fields or signals which are oscillating in step with the echo, but it can still refocus quasi-static dephasing noise. Of course, this is always, as I said, a compromise. So we are now able to still measure some signals, but they need to be oscillating. And in particular, there is a compromise between the frequency of the signal that we can measure with respect to the type of coherence time that we can achieve. So here what I'm plotting is the sensitivity in log scale with respect to the interrogation time. So as I said, what I would expect here is to have a 1 over square root of t type of law for a single quantum sensor, signaling that the longer I interrogate my system, the better I know what is the phase which is accumulated, and so how much of the external, what is the amount of the external field. However, of course, at some point I have noise, and so when I start having noise, my signal decays typically exponentially, and so here I have this blow up of my sensitivity curve. Now, if I apply some pulses, I might be able to shift the coherence time, so the point of where this inflection happens, a bit later in time. And so I can achieve a slightly better sensitivity. The minimum here is better than before. But of course, because I need to apply more pulses, the frequency of the field which I can measure becomes higher. And I can continue this, so I can apply many more pulses. In order for them to be effective, again, the rate at which I apply this pulse should be fast with respect to the correlation time of the noise itself. It's not that I can just apply more pulses for longer time. I need to apply more of them to refocus different parts of the noise. And so I can achieve better coherence time, so the minimum here is lower, but now the frequency of the field which I can measure is also higher. So it's really a compromise between the frequency of the field which I can measure here and how well I can measure them. And one can map out, if you want, the whole space. Here, the color codes the frequency of the field which I can measure, and the points here, again, represent the sensitivity. And again, depending on which type of dynamical decoupling, so which type of quantum error correction you're applying, you might have slightly different compromises and some which are better than others. So for example, here in this relatively old work, what we were comparing was pulse decoupling, the one which I described, in which you apply pi pulses at regular interval, with respect to continuous decoupling, in which you just drive your system continuously in order to, again, achieve sort of the same thing with respect to the pi pulses. You can think of continuous decoupling as saying you're putting your pi pulses closer and closer together until the point where there is no space in between them, and so you're just continuously driving your system. And what we found was that for continuous decoupling, we had a slightly better compromise between the frequency that we can measure with respect to the sensitivity. So you can see here there is a little bit more blue color coded, so lower frequency at the same sensitivity than for pulse decoupling. So as I say, this is the simplest possible example of trying to apply quantum error correction to protect a quantum sensor. And this has been used a lot, also in practical application, especially for NV centers in Diamond, to try to measure things going from single molecules, single spin molecules, to 2D materials like graphene, etc. But what we want to do now is to sort of ask some more general question. If instead of having just one single sensor, like one single spin, one single atom, if we have more than one, so some ancillas, can we actually find some more powerful ways of protecting the sensor itself? And also, here what we were doing, we were sort of trying to distinguish between signal and noise based on the frequency of the signal and noise itself. So we were able to erase sort of static noise, but preserve signals because they had the frequency. So frequency was sort of the discriminant between the two. So can we find different quantities, not just frequency, in order to distinguish between a noise and signal, and so be able to construct some quantum error correction strategies which sort of distinguish based on something else. And so with respect to the first question, of course, the first thing which comes into mind is to say, okay, instead of just using a single qubit for sensor, if we have a larger system, I can start to really apply some of the idea of quantum error correction codes in order to achieve better sensitivities. And this is something which has sort of emerged by now about 4 years ago. In 2013, a bunch of people started thinking about this question. And the answer was, yes, you can try to use quantum error correction to achieve better sensitivity. And so there were a few proposals. So the simplest one was, as I say, very, very simple. So the idea was to say, okay, I have a state, which is a GSE state, 0, 0, 0 plus 1, 1, 1. And we know that this will rotate at 3 times faster than a non-entangled a set of 3 qubits, and so it sort of achieves the Heisenberg limit with respect to the number of qubits for sensitivity in order to sense the phase estimation. At the same time, this also protects the qubits themselves against a bit flip noise. So if you have a bit flip, you can take a majority vote and still recover what is your non-perturbed, your correct state. So what you really have here is a very simple example of a quantum error correction code, which at the same time can be useful for quantum sensing. So more generally, as I say, there has been a few more proposals, and some simple ideas just involve one qubit used as a sensor, so which couples to the external world, and then one so-called good ancilla, so another qubit which is assumed to be completely protected against noise, so it doesn't couple at all to noise. And also because it's protected against noise, the assumption sort of goes hand in hand, but it will also not couple to the signal of interest. So you really have one system which is talking to the external world and one which is very much protected, it only talks or only couples to your quantum sensor. And so the scheme can be thought in a very simple way. What you do is to let your quantum sensor interact with the external field, and so acquire, for example, a phase, or in any case, some parameter which is a function, some state, which is a function of the external parameter. And from time to time, you apply some encoding and recovery operation in order to correct for a possible error which have happened during the free evolution time. And if you apply this recovery operation fast enough, then during all this time, you can achieve an almost noiseless type evolution. So now you can really extend your interrogation time for very long, and you go from having to repeat your interrogation many, many times, which give the square root of t scaling, to instead being able to just acquire the signal in one go, which gives your t type of scaling, so linear scaling. And so you go from, if you want, a classical type of behavior to the Heisenberg limited sensing type of behavior. These schemes, for example, was proposed in Michel Lukin group and was also correcting for bit flip error at rate alpha while measuring a magnetic field along the z direction, so a typical phase. And similar proposals were also given by Dur and Arad. Sometime the assumption was also to have just one good ancilla. Some other cases were having some larger codes, so more similar to typical quantum error correction code that people think about, in which all the qubits are subjected to the same type of noise. And also there's been some experimental implementation in the group of Fedor Jeleskov with also MB centers. If you notice here, and also in the previous case, what we have is that the error that we are applying is along one direction, so it's a bit flip. If you want, you could think about it as a sigma x noise, while the field that we want to measure is of the type of sigma z type of operation. So it seems to emerge that here, again, we need something to distinguish between signal and noise. And in this case, it's really the algebraic properties of your noise and your signal which lead to this discrimination itself. And what we can do is also to compare how this quantum error correction code perform with respect to dynamical decoupling. So the first thing is that dynamical decoupling is very effective if you have a non-Markovian type of noise. So you need some memory in your noise so that you have this cancellation of phases at different time. If your noise is Markovian, the phase which is accumulated very quickly doesn't relate to the phase which accumulated in the previous period, and so it's not really possible to achieve this decoupling. Instead, with quantum error correction, this assumption of non-Markovianity is not needed, and you can actually also correct for Markovian noise. Also, there are very different requirements that you need for the experimental implementations. So for example, for dynamical decoupling, the operation that you apply, the pi pulses, for example, need to be fast with respect to the correlation time of the noise, while in quantum error correction codes, you need to be fast with respect to the intensity of the noise, the rate of the noise itself. And for different type of environments, these two can be quite different. And so depending on what is your environment, one of the two strategies might be better. Also, as I said, the two types of schemes discriminate signal from noise based on quite different considerations. So as I said, for dynamical decoupling, what you really are implementing is a frequency filter. So you have a filter which has a bandpass around a particular frequency, and you select a signal which has that particular frequency, but it will erase all other type of frequency, especially low frequency, which are the one which are typically the most common, like think about 1/f noise, for example. While for quantum error correction code, if you want, it's more of an algebraic filter in which, if you want, the type of operator with which your signal and noise couple to your system are really what distinguish one from the other. So for example, you have a signal which is along sigma z, while you have a bit flip or a sigma x error. Not exactly the same, but one can sort of think about it in this way. So these particular requirements and if you want, a condition under which you can achieve some quantum error correction code have been very recently put on a very formal footing by two groups, in particular Yang Zhang here. And the idea was that if you have a system which evolves under some Hamiltonian, which encodes the coupling to the external signal, and some Markovian noise encoded by some Lindbladian operator, you can achieve, you can have an error correction code if and only if your Hamiltonian is not defined by the space spanned by the noise itself. And that sort of makes sense. So if your Hamiltonian sort of has very much similarity with the type of noise that you're trying to correct, well, your correction code will also erase the Hamiltonian itself. And so it's, if you want, a very intuitive type of result, but of course, one has to be careful in how you actually sort of like formulate in a more precise way this condition. So for my intuitive picture, what you have is that if you really have your noise to be in a space which is perpendicular to the space of the Hamiltonian itself, so the signal itself, then a quantum error correction code does exist. Otherwise, that it doesn't exist anymore. The problem here is that if we consider really for a single qubit sensor, this really reduces down to what I explained before. So what you want in the end, or what you seem to have in the end, is that what you want is a signal which is along one axis, while your noise is around a perpendicular axis. But this is not the most common scenarios when you consider practical experiment. So first of all, if you have some signal, typically there is also some noise associated with the signal itself. So maybe the signal that you have, you want to measure its average, but it also fluctuates, and that will induce also decay of your sensor. Also, as I said, if you know that your system is very much prone to bit flip error or dephasing error, most probably that's also the way that it couples more strongly to a signal. And so you would really like to measure things which couple in quite the same way. And so what can we do in order to sort of move beyond these at least simile requirements which have emerged from these I would say more like the original 2013 works, which have sort of like been thought as a limitation for this quantum error correction code. The idea is, as I say, to try to find some different ways of distinguishing or discriminating between noise and signal. So up until now, it was like the axis of the operators, but a different way is to think about the spatial correlation that the noise has with respect to the signal. So for example here, I consider a noise which has different values, it behaves differently. I teach individual qubits which form my quantum sensor, while I have a uniform signal. I could have, of course, the opposite. I could have a signal which is not uniform, and I could have a noise which is instead uniform. So the idea is that I will have different correlation among the noise, spatial correlation, which makes me able to distinguish with respect to the signal itself. So again, what we have is that we were using temporal correlation for dynamical decoupling. We were thinking of just using, if you want, spatial direction of your signal noise for quantum error correction, but also for quantum error correction, you can think more generally about spatial correlation of noise and signal. And so a simple example is, again, in trying to measure, doing, if you want, the phase estimation, so measuring a signal around the z direction, and do that still in the presence of the phasing noise, which is one of the noise which is the most common. So here I will have an Hamiltonian with a certain number of qubits, n qubits, and each qubit has a different coupling to your external signal represented by this omega I. So here I define a vector omega, which represents how your qubits in the sensor couple to your signal. And also we have some source of noise, and again, we assume that I only have some dephasing noise, so represented again by the same type of operator, with capital Z are the same as sigma Z Pauli operator, with some rate at which the dephasing happens, but also some correlation among how each qubit is affected by the noise itself. So this Cij can be encapsulated in a matrix C, which really represents the correlation, a spatial correlation among different qubits and how the noise affects the different qubits. So intuitively, what we want is that this vector omega is not describing the same type of correlation as the matrix C, which represented the noise itself. If the two are describe different type of correlation, we could expect that we should be able to distinguish between the signal, the effect of the signal on our sensor, and the effect of the noise on the sensor. And so we should be able to find some quantum error correction codes, which is able to cancel out this noise while preserving at least some of this signal here. So maybe it doesn't preserve it completely, it reduces its effect a bit, but it still preserves some of it. So more formally, what one wants is that this vector is not in the column space of the matrix here. And this condition is, of course, completely included in the previous condition found by other people. It's just that what we do is to look at things in a slightly different way. We look at our lim-ladder operator in terms of operation on individual qubits and not on the overall quantum sensor. And so this leads to a slightly different formulation, which sort of highlights this type of spatial correlation, which can help in distinguishing signal and noise. So we can, for example, think about the most simple possible system. So looking at 2 and 3 qubits. So for a 2-qubit sensor, I can only have a quantum error correction code for sensing if the noise between the 2 qubits is perfectly anti-correlated. So when this spin number 1 acquire a phase of +1, the qubit number 2 will acquire a phase of -1, which of course sounds quite restrictive. But then what we could think of is sort of like the opposite type of regime. So I have a noise which is uniform, so it's completely correlated between the 2 qubits, which sounds, at least for my experimentalist part, sort of like reasonable. And then what we are trying to measure now is a difference in between the energy which is acquired by qubit 1 and qubit 2. So we use our system as a gradiometer to measure differences in the field itself in the presence of a perfectly correlated noise. For a 3-qubit sensor, so if outside this condition, it's possible to prove that for 2-qubit, there is no other possible quantum error correction code which will give you protection, while at the same time allowing you to measure some type of noise, at least for this, like measuring Z, a phase along Z in the presence of dephasing. For a 3-qubit sensor, we can still measure a uniform Z field with the same repetition code that we saw before. But this is possible when we have some particular correlation again. So for each pair Cij, the correlation is -1/2 for dephasing. And in that case, it turns out that actually the code itself becomes a decoherent-free subspace. So you don't even need recovery operations. So the system becomes directly protected against this noise. And so you can just sort of like do your sensing without having to sort of interrupt the sensing itself by these encoding and recovery operations. Of course, these are cases which are sort of like quite peculiar. This one, okay, maybe I could think of trying to implement it in my NV experimental system. This other one with correlation -1/2 seems sort of weird. I mean, I can engineer some noise, which is like that for proof of principle, but doesn't seem particularly practical. For more general type of noise, then it becomes difficult to find analytically some error correction codes. But what we can do is to try to find numerically some codes which actually protect for any type of possible correlation, as again encapsulated in this correlation matrix here. So here what we did was for 2 qubits to try to find some error correction codes, either some real error correction codes, or active error correction codes, some DFS, or in some cases it was not possible to find a code at all. And so in order to find here, what we did was just to sort of bound how much, like put a lower threshold to how much of the signal we want to retain when applying this error correction code, and at the same time a threshold for how much error we want to allow in our system which is still canceled out by the correction code itself. And so there are sort of interesting bands where there is some DFS, which is possible, and other cases in which it seems that only an active error correction, where you need to implement also encoding and recovery operation, are instead possible. So these are quite recent results, which are now on the archive. So going back to the question which I had two questions. So one was, can we actually get some slightly better result exploiting ancillary systems? So I sort of already addressed a little bit this question, so find some new type of quantity which can discriminate between signal and noise. And what I told you is that, well, instead of looking at temporal correlation as dynamical decoupling, you could look at spatial correlation in your noise. And by using quantum error correction, you should be able to sort of find better sensitivity by protecting, encoding your quantum sensor in a logical space. Going back to this first question, now what we can ask is, okay, let's say that I still want to just discriminate noise and signal just based on frequency. And this is quite nice because it's been a very, very powerful tool for the experimentalists to just use dynamical decoupling to apply this frequency filter. The problem is that, as I said, typically you need to measure faster and faster fields, so fields of higher frequency if you want better and better protection. And not all the fields are actually oscillating in time. So can we find something else? Can we find a different result if you exploit some ancillary system? And the idea is really to try to sort of convert a field which is static, which is somehow the most common type of field that you can try to measure. There are a lot of signals out there which are actually static or quasi-static, which can be nicely approximated by static field, by sort of transforming it into instead an oscillating field. So we know that dynamical decoupling provides very good filters for oscillating fields. So can we find some other way, which is intrinsic to the quantum sensor itself, to do this up conversion from zero frequency to a higher frequency? And what we would like to do is to achieve this with something which is, if you want, at the quantum level itself. Of course, you could take your classical field and use some classical device to up convert the frequency, but this typically sort of requires some if you want a larger experimental apparatus, can introduce some additional noise, et cetera, et cetera. So we want to do it really at the quantum level. If I rewrite this picture in frequency space, I can put a little bit more of information here. So here I have in blue is the spectrum of my signal itself. Okay, so the signal itself might have some noise associated with it. So as I represented here, you also have some small oscillation of the signal itself. It's not just flat. And typically, what you would like to only measure is its average, so the static part of it. So what I have then is this signal noise spectrum. I have some bath, which will have some noise spectrum itself. Typically centered at some other frequency, although very often you also have a contribution which is 1 over f noise still along Z, so this is yet another contribution. And the simplest thing that you can do to measure static field is just to do a so-called Ramsey type of experiments, which is limited by T2 star. So here I'm also representing what is the width of the inverse T2 star, which tells you how much your noise you will be filtering out if you just apply a Ramsey sequence. And typically this is not particularly good, so you have quite a large width here. Now if I'm able to upconvert my signal, what I can do is to bypass completely the 1 over f noise. I can still shift to, for example, higher frequency than the bath, which I have here. And at the same time, I'm also reducing the filter of my of my control, going from the larger 1 over T2 star width to a much smaller 1 over T2, so the coherence time of your sensor under dynamical decoupling. So what we have is that if I can go from having a signal at DC frequency, so 0 frequency, to a signal which is now at some higher frequency, omega 0, which is this line here, which I want to measure. At the same time, I'm also converting the noise spectrum and also shifting that. But because I have a narrower filter here, the effect of noise associated with the signal itself is going to be less. So as I said, I would like to sort of go from this picture to this other picture by using something which is intrinsic to the sensor itself. And really, what we are trying to do is to do, if you want, a two-step protocol. So the first step is really to exploit an ancillary qubit to upconvert the frequency. And then in the second step, I would apply a dynamical decoupling sequence to filter out the signal from the rest of the environmental noise and also signal noise. So this is really equivalent to what people do in classical experiment with a lock-in amplifier. So the idea is that we have the signal, DC signal, we mix it with some reference signal, which is AC. We then apply some bandpass filter, which is centered around this reference frequency here, so that only the signal which is mixed with this reference field pass through and is then detected, but everything else is instead canceled out. So whatever is not mixed up with the reference signal is canceled out. So what can we do is to really replace this classical apparatus with a quantum apparatus, an ancillary qubit, which perform this same dynamical, this same upconversion, and then apply also some pi pulses to achieve the filter itself. So we did this using ambient centers in diamond, and I think that Tim is probably going to talk more about it, so I'm just reminding you that this is a defect in diamond with an electronic spin 1, which also has a nuclear spin associated with the nitrogen-14 spin 1 nuclear spin, which is our ancilla that we exploit in the system itself. So the two spin, the electronic and nuclear spin, are coupled by so-called isotropic hyperfine, so this Heisenberg type of interaction where S is the electronic spin and I is the nuclear spin. And because of the larger energy difference between the levels of the electronic spin, these two terms drop out, and so the N14 only cause a frequency shift, which is boring because it's always there and we can just cancel out very quickly. However, if I also add a transverse field, now I have some new coupling between the electron and nuclear spin, which emerges because of virtual transition of the electronic and nuclear spin. And so this looks like a coupling which is sigma ZIX, which is now an anisotropic hyperfine coupling, which is usually seen in dynamical decoupling experiment. If you want, what happens is that now my nuclear spin is oscillating its own Larmor frequency, so it becomes an AC field, and decouples in a way which creates a dynamical shift, but is also perpendicular to the energy itself. This effect is particularly strong if we work at a particular working point where the energy of the electronic spin is reduced, so that this perturbative term is much larger. And so we also implemented the experiments about this. Here I'm just showing you how we can see the signal as a function of time, or if you want, as a function of the number of pulses. I don't know what's going on, sorry. The number of pulses here for two different magnetic field, transverse magnetic field. So the intrinsic magnetic field, which we were not able to completely cancel out, gives you this slower oscillation, while if we add some magnetic field, you have much faster oscillation. And so what we show here is that if we were to change the voltage of the external magnetic field, we would see oscillation, which indicates that indeed we are able to measure this external field. Okay, so this brings me to the conclusion. So what I show you today is that quantum error correction is also good for sensing. So traditionally, people have used the simplest form of quantum error correction, which is dynamical decoupling, to achieve a discrimination between signal and noise based on the frequency. But more recently, some new ideas have emerged which really use quantum error correction codes for sensing. And I think that we are only starting to sort of scratch the surface of what are interesting regime for it. So there has been already some very solid results, but to couple them and make them practical for a real application, I think that we're only now starting to learn how to do things. So before really concluding, I want to thank the 3 students who actually did the work. In particular, David Layden has done the work on quantum error correction with spatial correlation, while Ashok Ajoy, who's now in Berkeley, and Ishan Liu have done the work on the up conversion, or if you want, the lock-in amplifier. Thank you very much.
Thank you, Paola, for the nice talk. So we have time for a few questions.